Today, we're going to talk a little bit about some of the things we've been working on in our lab and in collaboration with some other folks, both within Rutgers and the North Carolina State University. Deepti Salvi is the PI. We're co-PIs on a grant with the USDA. And so that is where some of the packaging will come into play. So our lab focuses kind of spread out on a few different areas. When I first came to Rutgers, I was excited about a lot of different things. I'm still excited about a lot of different things. We focused a little bit, and now we're starting to expand and look at some different areas again. But one of the main themes and one of the topics that's really kept our lives going over the years is that of disposable electronics and sensors, and in particular focusing on paper-based systems. So we'll talk a little bit today about some of these systems that we've been pursuing. Before we get into that, though, I'd just like to talk a little bit about this term we've coined of papertronics. And so this came out. Luis and others were there back in 2016. We had a workshop sponsored by the National Science Foundation here in the US. And the program manager was like, she has a program in spintronics. She's had different types of programs focusing on electronic devices. So she said, why not call it papertronics? So here's a definition, and there are a few of us that you'll sometimes see use this term papertronics. Hopefully it spreads a little bit more. But when we think of papertronics, we're thinking about some type of multi-scale fibrous material. Cellulose is, of course, one of the prime candidates, especially with this group of individuals and this conference. And then kind of maybe one more out there type of perception I like to think about is patterning flows. So when we take these substrates, we take these materials, it's an opportunity for us to tune how fluids, literally fluids, right? Heat, light, charges, fields, forces and stresses might be manipulated through our attempts to tune the properties of these materials. And in terms of what I hope makes this area transformative is the idea that by tuning one property and doing it over and over and over again, right? So we have scalable manufacturing processes. We are able to maybe get emergent behavior. We're able to get functionality that might not otherwise be possible, okay? And I am a big fan of printed electronics. I would probably get, well, we need to do some more in that area, actually, to integrate with some of the other things that we're doing. I'm also very interested in how we tune the volume inside the substrate itself, okay? And you'll see kind of a couple of different approaches, or maybe one approach really that's kind of in volume, and the other approaches are more on the surface. And then in terms of the tunability, you see this work from a few years ago, how they were able to essentially but they were able to manipulate coatings on the fibers, and in this case, using kind of an expensive printing process. And then for those of you who are very interested in cellulose and nanocellulose, you know that this is a hierarchical material, right? So starting from the nanoscale and going up really to kilometers when you start to think about the sheets and the rolls that get produced. And in terms of trying to think of international needs and addressing grand challenges, we still would love to be able to attack these different areas or leverage the exciting developments in them as well. So, and then these are some of the topics that you might find, and it's not limited to these, all right? But these are still, even from a few years ago, these topics are still things that we hope that papertronics will address. And if you're interested, you can take a look at a final report that we produced, and there's this kind of figure in there where we, with Andrew Steckel and I, and kind of a result of the whole participation in the conference, we kind of thought about, okay, tuning properties, then processes, then integrating these processes or materials, and then potential kind of big vision scalable devices and applications. So that's kind of an overarching vision for what we've been excited about doing. Let me talk about a few different things, and one is going to be our efforts in what we'll call paper-based skin. Now, we're not trying to replace human skin, but we are trying to make skin-like devices that have the properties that skin has. Okay, so and mostly in sensing, but another property of skin is it does provide antimicrobial protection. Okay? It's the largest organ on the body, all right, and so and it keeps things out, right? It helps keep microbes from causing us harm. Okay, and at the time, there was a lot of effort in making active cells, and I think, you know, still, right, we're seeing with printed electronics, we're seeing with OLEDs and a lot of different things. It's great to have active cells, okay, over large areas. We were looking at trying to do this in a more passive fashion. And this is kind of a diagram that describes that. So here's our multi-layered architecture. We want to be able to do touch sensing on the surface. We want to be able to do force sensing through piezoresistive layers. And then we also want to be able to provide antimicrobial protection. And that is kind of a very small kind of point right here, but generation of plasma, which we'll talk about a little bit in a few minutes. Okay, and these are some of the ongoing results. So this is for antimicrobial protection. Okay, that's the plasma we're talking about. This is kind of a snapshot of what you have when you make piezoresistive paper, and this is kind of a snapshot of the capacitive sensing that you can have on the outer layer. Right. So we haven't like published a paper with all three of these things integrated. We probably should work on that, but we have attacked each of these, each one of these kind of items in this multi-layered architecture with functional devices, functional layers. Okay, so the first one is how can we make these piezoresistive layers, and then so to do that we focus on using a tool that's common, which is embossing, right? So in our case, what we want to be able to do is understand the processing property relationships for tuning the conductivity of fibrous materials. And this will go into our kind of overall theme of skin-like sensing. And still argue that large scale kind of flexible sheets for doing spatial detection of force does not really exist yet. Okay, and a lot of folks have worked on this, and so please feel free to send me papers and things like say, no, they've got it. All right, I will argue still that we're not quite there. And we're trying to tune the volume of the substrates instead of just printing things on the top layers, which is probably the way it will happen or should happen. So to keep things cheap and more or less safe, we start with mixing carbon black with cellulose fibers. So of all the nanomaterials, or well, maybe not all, but of a lot of the nanomaterials, carbon black is kind of a low-cost entry point for us. And then we look at relationships between concentration, porosity, and impedance. Okay, and we've made some kind of sensors and prototypes. The idea here, again, this comes from a few years ago, that it's trying to put out there is, as we look at patterning flexible electronics, we see some wonderful efforts ongoing, great with transfer printing. We see ongoing wonderful efforts with additive manufacturing and inkjet or other methods of depositing onto surfaces. And what we were kind of still are interested in looking at is, what if you embed the functional materials in the substrate, in the volume, and you're able to emboss and essentially add conductivity or add functionality because you decrease the porosity in specified regions of your material. Okay, so that's kind of where we went, where we're thinking in terms of scalability. And you might argue that if you were actually able to do this in a roll-to-roll process, that it could be something that could be competitive to flexography or other printing electronic techniques. Okay, and so this is kind of the basic overview that we came up with. Very simple idea. So that you start with a highly porous material with embedded particles. And in this case, if we're interested in conductivity, when you squish it, right, when you emboss it, you can potentially bring these things closer to each other. And we hope that we can find percolation or that get through percolation to be able to get, and that's a kind of an interesting term here, because this is a three-phase material, and we are controlling not only the concentration of the nano material in the larger network or matrix, but we're also looking at what happens with the volume and the density. Okay. So this is kind of a process, and you're welcome to learn more about it or send me questions if you like. But essentially, we start with some type of cellulose fibers, and we have some type of carbon black, and then we also use some foaming agent to reduce the amount of water. Okay, but now you have this foaming agent, so right, it's tricky when you're doing these things. What are the trade-offs? Less water, and now you have a surfactant, right? And then we use a hand sheet former, which is kind of the way people make paper. You can buy mold and decal. That's how we started, off of whatever, some popular website, and you can make your own paper by hand too. And then after doing that, we take or after pulling vacuum and after making the paper, we can do embossing here. Okay. And these are some of the types of materials that we get. These are sheets. You can see as you increase the concentration of carbon black, they get darker. And then we have a really nice old school HP impedance analyzer. Does a great job of testing our samples that we make like this. And you can see, okay, if I make it more porous, right, it looks a little bit thicker, a little fluffier. Make it less porous, right, it looks a little more compact. These are some of the SCM images that give you a qualitative perspective on what's happening. These are uncompressed. And then in the red, you have concentrations of carbon black. This is compressed, all right? And, it's a little hard to see, but as we increase the concentration of carbon black and you get a little more clumping and stuff, you can kind of see that you get kind of more of this interesting coating and stuff on the fibers, and it gets a little bit grainier looking. But these are, you can argue this is kind of grainy too, but that's just the artifacts of the SEM or the roughness of the cellulose itself. And then we can make things where we emboss patterns. Okay, it's maybe a little bit hard to see here, but these are different electrodes that have been embossed, and so these are conductive here, and then the fluffy areas are where it's more insulative, right? And then as you bridge the gap with touch or contact, we can see jumps in effective capacitance. I guess this is just to show that this is in fact works, and I think this video is also online and a supplementary information if you're interested. Okay, so here's some takeaways here, that we can in fact tune the volume of these paper-based devices through embossing, and we can affect changes in the porosity, okay, that will have an effect on the conductivity of the material. And the conductivity, I didn't have everything on the percolation threshold and those measurements, but you can look those up online if you like, but we do have a factor about a 300, okay? And if we were to use nanotubes or other materials, we'd have much higher increase in absolute conductivity instead of kind of the modest, shall we say, conductivity that or conductance that we're able to get with our devices. Okay, so that's one aspect of what we've been doing. Another aspect is that antimicrobial protection. And in this case, we accidentally kind of ran into something called dielectric barrier discharge. And what happens here is you apply a high voltage, oscillating voltage, between a pattern electrode and a grounded electrode, and you're able to induce what's called cold plasma. And it creates a variety of species that are able to kill bacteria and microbes. So in light of the time, I will go through some of this quickly. All right, we're definitely not the first to look at using cold plasma to kill things and kill microbes. And arguably, actually, it may even begin before Professor LaRusse, who's at Old Dominion, and he'll be happy to talk to you about this kind of interesting, exciting field. And our collaborator has been involved with what's called plasma activated water, but this particular research has focused more on what we would call dry cold plasma. And here's a diagram that kind of lays out how we go about making our devices. We have a layer of metallized paper and another layer of metallized paper, and then we have an insulator in between. And we pattern one of these layers. Usually the layer that you see is the layer that's patterned. The bottom layer is just a complete sheet of metallized paper. Okay, and if you're interested in the type of metallized paper we use, I actually started using this material back when I was a postdoc. And using a conventional laser cutter to pattern it, we were able to make touch pads. And this is kind of an example of an alarm or a keypad for a box, if you like. Okay, so the plasma itself gets generated where you have high concentration of electric field. Again, hand waving. We're working with a plasma physicist, and every time we talk, it seems like I learned something new about this crazy stuff. But you can see that the plasma is kind of glowing the most around the edges, the inner edges of these honeycomb structures, right? And we call this, and I think others will argue that this is kind of a surface plasma. And then we called the stuff in between, inside the device, volume plasma. And now we believe that we have much less volume plasma than surface plasma, okay? But nonetheless, I think both are kind of there. And then you probably can't hear this, but this is an example of a device, one of the early ones that we created. And it's also dependent on the frequency that you apply to the device in terms of being able to light up the different cells that you have here. Okay, so we've been able to do things like kill bacteria that we've kind of artificially sneezed onto a surface. And so the paper is called paper-based sanitization. Okay, so if you're interested in this area, you have sanitization, which is kind of the bare minimum, like you do something, right? Like hand sanitizer, right? And that's like 99% or 99.9%, right? That's like sanitization. And as you go further along, you get to disinfection, and then finally you get to sterilization. Okay, so 6 log is kind of what's considered sterilization. We're kind of like this. The early results we produce like 2 to 3 log, and depending on the surface and the substrate, we can get to much higher. We can get to like 5, 6 log, but it depends on different conditions and exposure times, and it's interesting. And we're still in this area. Another thing that we're kind of excited about is the multifunctionality of these. Again, skin-like sensing, right? So here's something that can kind of act as a touch sensor. All right, so these are capacitive pads. But then if you were to shut shut off the capacitive sensing through, like in this case, this is Arduino, and then apply the high voltage, right? You can kind of make it glow, and you could think of making like self-sanitizing touchpads. And then what's been fun of late is looking at how we can inactivate bacteria on fresh produce. So we know that like E. coli and Listeria and staph are problematic, right? And can cause people to get sick. So with Deepti, Salvi at NC State, we've been working on reducing or being able to get rid of differing degrees of bacteria. So here, right, on tomatoes, which are smooth surfaces, we're like approaching 5 log, all right, when we are looking at killing E. coli. But if you have Listeria, we're not able to kill as much, right? So why is that? I would like to know. And if we're going to come up with solutions for food, we're going to need to be able to kind of treat a wide array of potential microbes. And then we can do things where we look at ozone, right? So in this case, as you would expect, ozone is going to increase as we increase the amount of time we run. So this is the amount of time we're running our device, activation time. This is the total ozone that's produced. So the container, how you enclose what you're trying to treat is also very important and has an effect on things. And the food quality is another concern for the folks that are interested in fresh produce, right? So this is, we have like control, right? This is our tomato. This is another tomato that's been treated for 2 minutes, and 10 minutes. And at least tomatoes, they stand up pretty well to cold plasma. Spinach, which I didn't show here, doesn't like it as much, all right? So these are some of the other questions that we have to address. Here's some takeaways, right, for our paper-based sanitizers. We would like to be looking at, and kind of one of the things we're interested in is looking at, okay, is the plasma that we generate going to damage electronic devices? Could we make little packages or little pockets that you put things into and you kill, just like these like little UV light things that people, these little UV light containers that people can buy, or UV light robots, right, for sanitizing transportation related vehicles. So these are some of the exciting things that we're looking at. We have a project with Francois Berthiaume in biomedical engineering where we're looking at wound treatment as well. Turns out that the reactive species, they interact with the physiological pathways associated with wounds. So that's kind of an exciting area as well. The last thing, and I guess I can talk about this pretty quickly, is the idea of using paper as a substrate for robotics. In this case, using it for pneumatically driven robots. But there are opportunities to look at other types of materials or other types of actuators that would be using paper. And of course, those of you following like some of the nanowood and some exciting developments there, paper or wood-based materials can have very high strength. You think about the Wright brothers and those early folks that were working on flight and balsa wood. Balsa wood is still an excellent example of a material that has high strength to mass ratio. So that's one thing that we've been looking at here, using Yoshimura patterns, and then being able to inflate them and being able to characterize them and make them do things like walk very modestly like this, or be able to do things where they can pick things up, right? And also be able to do a modest, very modest level of manipulation, as you see here. I'd say that our kind of our contribution here is probably just in the simple idea of being able to compensate for the rotation of these Yoshimura patterns. So what we do is we take one and then we put another with opposite chirality, and so that when they expand, they're able to have a net zero rotation. Okay, so that's probably, so for things like this, where you have like 3 on this platform, that's a very useful thing, because otherwise you get these things that will jam with each other. Okay, so anyway, these are some of the takeaways for paper robotics. They have a modest payload to weight ratio. And when I say modest, it's actually better than the muscle, but that's not including the mass of the pumps, right, that we have. So, but if you just take a look at the mass or the power, or the ability to handle payload versus how much they weigh, we do quite well. And then we've also addressed kind of some of the stackability issues here. A flexible future for papertronics. All right, so yeah, we're excited about being able to take advantage of the porous structure of these materials, the multi-scale nature of these materials as well, and you know, I think I'm very open to different classes of materials and different suggestions. And as we get to these different classes of materials and different fillers, we're going to have to figure out how sustainable are these things, right? I mean, you know, and that's often probably, well, I don't know if you all receive that kind of feedback, but that's something that people, you know, want to know about. It's like, hey, you're putting all this nanomaterial in there. What does that do in terms of the recyclability? I think there's a lot of interesting stuff happening with the chemical activation of cellulose. I didn't talk about our biosensors, but being able to functionalize it to be able to detect small protein binding events and then address those through electrochemistry. That's something that we've been working on quite a bit, although we haven't published the work yet. And then you have tunable mechanical properties, and we talked about tunable conductivity, and we hope it's renewable. So thank you for taking the time to listen to this presentation and our work.
Okay, thank you very much, Aaron.